Hello everyone and welcome to lesson number 1 of this course, in which we're going to talk about data structures in Python and in general. Before we start talking about data structures, let's talk about what we know already with regards to data types and how data is stored in memory. If you have completed the previous course, or if you've done any Python or any programming before, you know that when we store data and when in our programs, it has a certain type, whether we have to define it or not. In Python, for example, we don't have to define it. We can just say number equals 5, and Python will automatically know that this is an int. And likewise, if we say number equals hello, Python will automatically know that this is a string. But we could manually convert types, and we could manually find what type it is. So if I run this line of code, print type number, type is a function which returns the type of a variable that is passed to it. Let's comment out this for now. We will get class string. So the type of variable number is string, which is expected because we are storing string in it. And if we had 5 in it, it would be class int, and likewise for every other type that we have encountered so far, like a boolean or a list. Let's try a few more. True, it's a bool, and let's try a dictionary, and we get class dictionary dict. So everything works as expected. So each data in computer has a certain type. Obviously, at the lowest level, everything is stored in binary as ones and zeros. But at a slightly higher level, at the programming language level, we define information that we store in data types, and that help us know what we are dealing with, whether we are dealing with strings, whether we are dealing with numbers, whether we are dealing with lists, dictionary sets, etc., etc. I just remembered we haven't actually covered sets, but sets are exactly the same as dictionaries, except for they are not mappings. They are not mappings from one value to another. They are just a list of values, but they're not ordered. So if I had a few words like apple, banana, and orange, it would be type set, because you can see it's very similar to a dictionary, but it's not a mapping. It's just a set of values. In this case, a set of fruits. So those are the fundamental types that are readily available in Python, but we can also create our own types. So as we know, we can create classes. So here I have just created an example class called board. Please ignore my naming convention here. I'm not, it's just not a good naming convention. Let's actually rename it class person, and it's going to have a name Bob and age 42. And let's create a person class, and let's find out the type of that person class. And let's comment out this for now, so it doesn't interfere. So we get that the data type of variable person1 is actually main.person, so it returns the data type to be this class. If we wanted to find out the type of one of the data points stored inside the class, for example, person1.name, it would return a string, because name inside the person class is indeed a string. Anyway, all of that you should already know. It was just a quick refresher. The beauty of programming languages is that you can build from the fundamental pieces up and up and up and up, and you can connect them together to build something more complex and more complicated and more useful. And that's where data structures come from. We have fundamental data types, obviously at lowest level 1 and 0s, and we can combine them together to store information in exactly the way we want. Obviously, we have seen it being used in classes before, but there are some very common ways to. There are some very common ways to store data, and some of which we are going to discuss today. Let me comment this out, and let's move to these. These are called derived structures, so they're not fundamentals, they're not readily available, although for Python, for example, you can import them and you can use them, but it is important that you understand how they work fundamentally in order to be able to use them efficiently. In today's lesson, we are not going to cover every single data type there is, because there's just so many, and you will have to learn that in your own free time, but we will learn a few, and hopefully the ideas will help you understand how data can be stored efficiently, and how different data types are useful in different scenarios. The four different data structures we're going to discuss today are trees, hash maps, stack, and linked list. And each of them is unique, and each of them is useful in different scenarios. So first, let's have a look at tree. And just before I explain it to you, this is not an actual Python code. This is just me demonstrating in a diagram how it looks conceptually. In memory, it would be stored differently, but it's important to understand these data structures conceptually and have a visual image of them, because you're not a computer. You will not be able to deal with data like a computer does. So what is a tree? A tree, as the name suggests, comes from real life tree. It has a root node where the tree starts, and then it has branches from this root node. In this diagram, we have a binary tree, which means it only has two nodes, two children. Each node only has two children. At maximum two children. It cannot have more than two, but it can have 0 or 1 or 2. But obviously, depending on the current scenario you're working on, you could have more children for each node, if that is what you were trying to implement. In this current diagram, we are storing numbers in this tree. We are storing 10. It has two children. Left children is stored 5. Right child has number 14. Number 14 has no children, as you can see, and node with number 5 stored in it has two children again, 3 and 7. The terminology with regards to trees is as follows. There are three terms you need to know. First one is the root. That's where the tree starts, and when you get the tree data structures, that's the only piece of information you know immediately. You know the root node, and from there you can find out the left and the right children, or more if you have more children. You have branches. These are what connects the nodes, and you have leaves. These are actually nodes in themselves, but they're not a root nodes. That's why they have a different term associated with them. So every node that is not a root node is called a leaf. So this would be called a leaf as well. So a good question arises: why are these useful? Why would we want to store data in such a manner? Well, obviously, there are many different scenarios where this can be used, but in this diagram, I have already sorted a tree. So as you can see, every single node is sorted in a way that the left child of this node is smaller than the value in the node, and the right child is larger. So as you can see, 10 on the left is 5, which is smaller. 14 on the right is larger than 10, and the same for 5. 3 is smaller than 5, and 7 is larger than 5. So if we stored these 5 numbers in a list, it would look something like this, assuming it was sorted as well. 3, 5, 7, 10, 14. And we wanted to find the smallest number in this list, or this tree of numbers, or this largest number. It would actually be more efficient to do it in a list or in an array. To find the smallest number, we just look at the first value, while in the tree we have to go down one node and then down another node, and only then we would find the smallest value is the same for the largest one, 14. In this case, 14 would be immediate as well. But as you can see, in this case, scenario, list is more efficient. So why would we use trees in the first place? Well, that's because I intentionally have chosen a scenario where lists outperform trees. And that is a very important notion that you need to understand. Different data structures are going to be useful in different scenarios. So now let's look at a scenario where data structures are, tree structures are actually more useful, and the one we're going to look at is actually the one you're looking at right now, and that is your computer. So in a computer, all the folders and all your documents are stored in a tree-like structure because that's natural. You have a root folder which has some folders, which eventually leads to your desktop, which you look at every day, and your desktop has some more folders, some folders have more files in them, and so on and so forth. It's a nested data structure, which is very useful to keep in a tree structure, because then we know how to get from each point back to the root, and from root to any other point. Everything is interconnected. So if we were to, just to demonstrate how it looks, let's say this is a desktop. Obviously desktop would not be your root node on your computer, but just for the purposes of demonstration. And you would have some folder called maybe, sorry, I'm not sure what Atom is doing here. Maybe we would have a folder called homework. And you would have another folder, another file called picture.jpg. So on your desktop you would have a folder called homework and picture.jpg. And inside your homework folder you would have english.pptx, because you're preparing a presentation for your English. And you had another image, for example, english.png. So as you can see, this is extremely useful to be stored in a tree structure, and it is what is used in computers nowadays. All the files are stored in a tree-like structure, starting from the root and leading to wherever you need to. And that's why trees are so important in the scenarios where they are useful. I actually left an error here for a tree. That's because we will actually have a look at how to implement trees in Python in a second, and we're not going to look at every single function implementation. We will just look at the basic bare bone tree, so that you understand how it's all interconnected. And we will do the same for LinkedList, but we'll get to that. Now let's talk about a Hashmap. So Hashmap is very similar to dictionary. Dictionary just maps a key to a value. It's a key-value pair and a whole dictionary of them. The reason Hashmap is different is it has a very special key, and the way we derive a key for each information value, is we take a hash of that value. So if we wanted to store number 47 in our Hashmap, we would actually take a hash of 47 and use that as key for that number. Why is it useful? So that when we want to find whether 47 is in our hash map, we don't have to look through every single value. We can literally just calculate the hash of 47, which is usually way quicker than looking through every single value in our dictionary or set or list or whatever data structure we would use otherwise. And then we would literally just find it immediately. So the time complexity of using Hashmap is how long it takes for a hash function to complete. And you might have heard about hash functions from blockchain, because blockchains quite frequently use hashing functions for many different purposes. And what a hashing function does is it converts whatever piece of information you have into a hash. And there are different hash standards, for example, SHA 256, I believe it's called, converts whatever you give it into 256 binary numbers. So it will be obviously 256 of these, and that will be a hash of your piece of information you have provided it. And while that looks a bit complicated, it truly improves, it incredibly improves the efficiency and the performance of your program, if that is what you're looking for. And again, if you're looking to use hash maps, I believe Python already provides it. It doesn't provide it by default, but you can import a library where it helps you. It provides all the functionality you need to use it. The third data structure we are going to talk about in this lesson is a stack. And the stack, I have drawn it vertically, but you could say, well, it just looks like a list, but flipped from horizontal to vertical. What's the difference? 1, 2, 5, 8, 4. The difference between the stack and the list is a stack has the following rules. Whatever comes in first leaves last. So in the list, we just store information, but in the stack, we are expecting this information to come and go. So if you put a number on the stack, let's actually do that now. This stack is a size of 5, by the way, but obviously it can be whatever size you want. Now we are looking at an empty stack, and if you want to put number 1 on it, it's going to go up here. Now, what if you want to put another number here? We will actually remove 1 from here, put it into the next cell, and add the new number we want to add right here. And if you wanted to add another number, again, we would repeat this process. Move everything down, and add another number. That's how we are adding information to stack. And if we wanted to remove information from stack, we couldn't just access directly into the box we are looking for like we did in list. We would have to pop information from it. And popping happens from the top where we were putting values in. So if we wanted to pop the value, we would remove the top one. So the last one we added. So this one would be removed and everything below would move up a notch. As such. Again, depending on scenarios, this might be what you're looking for. It might be just a waste of time. One useful use case for stacks is actually the undo button in any program. So whenever you're editing a Word document or preparing a presentation, you've done something and then you're like, oh my god, I didn't want to do it. I'll just Control Z and go back, right? So all your actions are actually stored on a stack. And whenever you want to go back, it will just look at that stack and remove the top value. So the last action you did will be the first one to be removed. So for example, I printed Word hello, and then I added a picture. And let's not use Python notation. And so first I added the pictures, then I printed hello. But if I wanted to reverse these actions, I would want to go in the reverse order. I would want to Control Z print hello first, and then I would want to remove the picture I added. So stacks are useful whenever you want to store the information in a way that you will access in reverse order. And the last piece, the last data structure we're going to look at today is linked list. Linked lists are mostly used in programming languages like C and C++, where pointers are commonly used. But it's an important data structure to understand as to how it works. So what a linked list is, it's the same as a list, but it's not all stored in a single piece of a single place in memory. Each element in a linked list has two things. First, it has a piece of information you're trying to store, and second, it has information regarding where the next element is. Hence why I used arrows here. So first element in linked list has two things: piece of information and information about B. And B has the same. It has a piece of information and information where the C is. So element number A has no idea where element number E is. In order for you to get from A to E, you would have to go through A, B, C, D, E, and eventually once your linked list ends, it will point to nowhere. None is a reserved word in Python programming language, which refers to no piece of information. You might have heard of null. I'm not sure if Python has that, probably not. So null or undefined, so it's basically, in binary it's 0, 0, 0, 0, certain number of zeros, and that's reserved reserved place in memory, which just means there's no information here. So that's a linked list. And again, whether we want to use it depends on the scenario we are currently working on. One useful scenario I'm going to talk about is shift tabbing on your computer. So you have many different windows open on your computer and many different programs, and usually you want to switch between them very quickly, and you can just shift tab. Shift tab switches from current program to the next, and from them to the next, and from them to the next, right? Actually, in most operating systems today, we would actually use doubly linked lists. So the only difference between linked list and double linked list is that you not only have the information regarding the next element in the list, but you also have the information about the last one. And the last element in this case would not point to none, it would actually point back to A. It's very difficult to represent in Atom, but you get the idea. So E would point to A and A would point to E. So it would create a complete loop. And basically what it means. What it means is in scenario like shift tabbing on your computer, whatever operating system you use, I think it's implemented in most of them, you can just shift tab or shift, it's actually command tab, I think, or control tab, depending on the operating system. I'm not sure which one it is, but you get the idea. You can quickly switch between different windows, different programs using a shortcut, and that's where such a data structure would be extremely useful, and that is probably what they use for such a scenario. Anyway, so those are the 4 data structures which I wanted to talk to you about, and there are many more. I implore you to go and explore and try to understand them further, and to truly understand them you will really need to implement them, and we will just look at a bare bone implementation of 2 of them right now, and I'm just commenting out all of this so that it doesn't interfere with our code running. So the first implementation is a tree structure. Looking back at the tree, we have a root, and then it has children. It has leaves which are connected to the root via branches, and it can go on indefinitely. So the way we could define it in Python, obviously if we didn't want to use an external library, and if we wanted to understand how tree structures work from the very beginning, we would create a class called node, or you could call it something else, but node is a generally accepted name for node in a tree, and we would define it as follows. So this is a constructor method in our node class, and it's going to take a piece of data which is going to be stored in our node, and it's going to take nothing else, and it will create 3 data points. It will create self.left, self.right, and self.data. In self.data we're going to store the data that we passed to this constructor method, and in self.left and self.right we're not going to store anything. We're going to just point to null location in our memory. So when we construct a node, it by default just has a piece of information and no children. And we have just implemented another method called print tree right here, just to print our tree once we actually populate it with some information. This print tree method actually uses recursion, which we haven't learned yet, but we will look at it in later lessons, so we're gonna ignore it for now. But all we need to understand for now is that it will print every single node which has data in our tree once we call this function. So now let's actually create our tree. So we create root by calling the node class and passing 10 to it. Then we create left by creating another node class, an instance of a node class, and pass 5 to it. And we connect these 2 together by saying root.left equals left. So we are saying instance of node class called root, and the data point .left in it, we will store our variable left in it, and in right we will store node 14, and then we're gonna print the tree. And this what's printed, it prints 5, 10, and 14. So the way our print tree function works is it prints everything on the left of our root node first, then it prints the root node, and then everything on the right of our root node. So actually, if we were to do left.left equals node 2, this would happen. Actually, I realize this is a bit confusing, so I should probably draw a diagram to show how it's stored. So line 77, we create a root and pass it 10. So this is how it happens. We created a root with 10 and it has no children. It's empty. All of the children point to none basically, hence we're not going to see them. Then on line 78 we create another node called 5. And again, it has no children. This line I'm going to comment out for now for simplicity, and then we say root.left equals left. So we are saying get this variable, which is this tree, and for the left child, connect the left variable to it. So we're basically connecting this up here in this point. So let's do that. 5. So that's what happened on line number 80, and on line number 81 we're saying connect to the right one, another instance of our node class with data 14. And that's how our tree would look like conceptually. Obviously in memory it's going to be stored slightly differently. And then we just printed the tree. And now uncommenting this line, we are saying left.left. So we are saying left.left equals 2. And we're just adding 2 there. And obviously we could go on indefinitely, but this is just a bare bones tree and data structure showing you how to create and populate tree. Obviously in the finished version you would have much more functionality implemented, like sorting algorithms, like inserting methods, like deleting methods, like self-balancing functionality. So if a tree is very unbalanced, so for a very unbalanced tree is when a lot of data points are on the left, and there's, actually let me rephrase it, a very unbalanced tree is when the height on one side of the tree, the height of the tree on one side of the tree is much different from the height on the other side of the tree. So if we had many more data points here, I realize doing it in Atom is not the best, but as you can see this is an unbalanced tree because the height of the left node is 3 while the height of the right node is 2, and obviously the more unbalanced the tree is, the less efficient it is when we're using it in scenarios like searching for information and so on and so forth. So that's about trees. And the second data structure I want to talk about is linked list. For implementing linked list, I actually did 2 different classes. First one which is going to represent a node in a linked list, and second one is going to represent a linked list altogether. First, let's have a look at a node in a linked list and not worry about anything else. So similarly like in a tree, a node in a linked list has a constructor method which takes some data and is going to be stored in a data field, and it has next, which is going to point to the next element in our list, and by default it's going to be pointing to nowhere. And we just have a wrapper function which is going to return the piece of information stored inside that node. And now let's have a look at the second class, a linked list. Its constructor method will not take any variables. It will just create a head, which by default points to nowhere, to none. And the reason we do that is just to initialize the variable, and we want to give it some value so that it is initialized. And again, the wrapper function will actually go through the entire linked list, and it will print it. And now let's actually see how we can use it. So on line 109, we are creating an instance of a linked list of this one, and we're not passing anything to it. So with this line, what happened is we just have head pointing to none. Actually, I think it's not even pointing anything. I think it's literally just none stored in our head variable. And then we create a node called A. So now we create, I should probably be writing it below all of this. Okay. None. And then we create a node which is gonna have A in it. And we store this node that we have created inside the head of our list we have just created. So in this list we are saying head equals node. So what it will do is it will remove A with A points to none. And then we will create a second node, B again, and we will connect the first node to the second node. So first.next, we will store B in here. That's what's going to happen. And then we will just print the list. Let's print it to see what happens. Let's comment out my diagram. And that's what we get. We get A, B, and point to none. And let's just create a third equals node C. Second.next equals third. And let's print the list. And we get A points to B, points to C, points to none. And that is how linked lists are implemented in its bare bone situation. But obviously, again, it's the same with trees. If you wanted to have a fully functional linked list, you would have to add much more functionality, such as inserting, such as adding, such as deleting, such as sorting it, and so on and so forth. Anyways, that's everything I wanted to talk to you about today. The general idea that is the most important to take away from this lesson is that there are many different data types out there, and it's important to know about as many of them as you possibly can in order for you to be able to analyze the problem you're currently working on and choose the appropriate data type for whatever it is you're currently working on. I encourage you to explore more data types. I encourage you to work with them. I encourage you to try to work with them from scratch and not just import them from an external library, because obviously external libraries already provide most of these. In fact, everything we have discussed in today's lesson is provided by external libraries. But you will not be able to use it efficiently and effectively unless you truly understand how it works at the lower level. So that's why I believe it's important to practice it at the lowest level first, and before going to higher level and writing more complex code. Anyways, that's it from me today. Thank you for watching, and see you in the next lesson.